Hey, welcome. Today we're going to be talking about how to solve conservation of energy problems with conservative or non-conservative forces using calculus for AP Physics classes, so mechanics or E&M. So let's go ahead and get to it. First of all, I do want to point out with this animation here, you can see that the dog is free to go back and forth and there is no friction like you can see over here. And as a result, no energy is being lost to the environment as heat or as increased thermal energy, so to speak. And as a result, you just have this switching back and forth between kinetic and potential energy. In any case, this is a visual reminder of what we're talking about when we talk about conservative forces. Two very important examples would be gravity and the spring force for mechanics classes. So gravity is acting like a conservative force here. I will say too that we had talked about how this work that any conservative force does is equal to a negative change in potential energy for the system. And that hopefully makes sense here if you think about it. That work done by gravity, for instance, is equal to a negative change in potential energy for the system. I do want to mention that I did this animation from PhET. You all should check out PhET. I'll put a link up to PhET in the description for my video. It's a fantastic website that does a lot with education through simulations. Alright, let's take a look at the second example I wanted to point out. This is demonstrating non-conservative forces here. So notice that friction is significant here, you could say, and as a result we do have thermal energy that inches up. And it does matter in terms of the path that is taken for a non-conservative force. In other words, it would matter if this person went back and forth like 1 time versus 50 times versus 100 times. That does matter because that energy is lost, a little bit of energy is lost to the environment as friction, which converts into thermal energy, and so that leaves less and less energy for the systems like kinetic or potential energy. So this is just a visual reminder of what we mean with non-conservative forces again. Alright, so let's go ahead and continue with what we were talking about previously. We said that work for a conservative force is equal to a negative change in potential energy. This is not on your equation sheet, so be careful with this. This equation over here is on your equation sheet, so we got to start with this and branch out to be able to solve for things. One of the things I want to do first of all is mention that this dr, I'm going to change this to dx throughout our work here, but just be careful with that in the sense that r could be substituted for x here. And so one way to think about this is let's take this value right here. This says the integral of force dot dr with respect to the position, the change, infinitesimally small change in position, so to speak. That is going to be equal to our work that's done. So I'm going to go ahead and take this and sub that into this equation right here, and let's think about what we have as a result. What we're going to do next is try to ask ourselves, alright, well, let's just look at one infinitesimally small area. So if we take this is an integral, we could say, well, what if we wanted to do more or less the inverse operation and convert this into a derivative? How would we go about doing that? Let's take a look. If you were going to do a very, very infinitesimally small area, you would multiply a force times a very small dx, and that would be equal to a change in the potential energy, du. Well, if we continued with that and we isolated for f of x, we would get a negative du over dx. And this is a negative derivative of the potential energy. So this is really, really crucial, this equation right here. It is not on your equation sheet, so be careful with that. But it is important to note that the force that causes a change in potential energy is going to be equal to the negative derivative of potential energy with respect to x. So let's take a look at an example problem for this. So it says if the only force acting on the object is given. So now we're going to have an equation here that's given for this and is conservative. What is the object's change in kinetic energy as it moves from 1 meter to 2 meter in terms of the position? Assume the force is in the x-axis. So how would you approach this problem? What do you think we would do first of all? Alright, well, one thing we could do is just write the equation that we know and sort of jog our memory with this and start thinking about this. We do know that you can integrate. We do know from the fundamental theorem of calculus that you can do the opposite operation, so to speak. But here, we can just integrate. That's all we need to do is take the integral of this function with respect to position given our upper and lower bounds. And so we go ahead and do that and we're going to solve and get an answer here of minus 1.5 joules. Now you could say, why do we get a negative 1.5 joules? How does that all work out? Well, that would be like a block that slides and it runs up against a spring that slows and stops the block. Alright, so fair enough. Let's try another example here and take a look at this. The example problem says if the function for the potential energy of a certain spring is given by this equation here, and I do want to take a moment to say this is on your equation sheet. So this is the potential energy for a typical spring is going to be governed by this equation over here. And if we continue the problem, it says then find the equation for the force for the compression or expansion of the spring. What do you expect we'll be able to do here? Alright, and so in this case we're going to take the derivative, the negative derivative of potential energy with respect to x. We go ahead and sub in our value for u here, and we could say, well, what is that equal to? We continue with some work over here. The 1/2 in front is going to be canceled out by this 2 right here, and what do we end up with? We end up with the force for this spring is going to be equal to minus kx. Well, this turns out to be Hooke's law. This is on your equation sheet as well. The negative sign is there to represent the fact that the force is in the opposite direction of the displacement. So this x value is kind of like a delta x here, or the x with respect to the distance from the equilibrium position for the spring, you could say. In any case, this is confirmation that these two equations are linked to each other. You can take the derivative of one to get the other, or the integral of one to get the other, so to speak. Alright, and lastly, I do want to point out a more general and a very useful equation for conservation of energy would be something like this. You could say kinetic initial plus potential initial plus the work that is done that's non-conservative, typically friction, is equal to the kinetic energy final plus U final. So let's think about this for a moment. This example was like one of the animations I showed at the beginning of the screencast where the girl on the skateboard got lower and lower. In other words, some of that energy is lost. That non-conservative energy leaves the system, and so we can keep track of that with this equation here. So as a result, this is a very useful equation. It's worth memorizing, not on your equation sheet. So in any case, hopefully this has been helpful. If you have any comments down below, please let me know, and I hope you all have a great day. Take care.